Well, you see, I keep wondering uh, what truly happens to us when we imagine stepping outside the gentle flow of time. If you were given a doorway that let you wander into yesterday or drift softly into tomorrow, would you take that first step? And um, as we sit here together, just you and me, I suppose there is something quietly extraordinary about the idea itself. Time travel, it sounds like a tale from old stories, and and yet it's stitched into the fabric of real physics, woven through equations that whisper about space-time as if it were a landscape rather than a ticking clock. And that feeling, well, it grows the more you think about it. Because once you start asking what time actually is, the universe begins to answer in ways that are not just scientific, but also deeply human. Perhaps that is why people from every corner of culture return to these questions again and again. What if the past is not, well, not really gone? What if the future is already there, waiting? And why do these ideas stir something inside us? So, um, uh, something like longing or awe or a faint memory of a place we have not yet visited. You see, you see, the science is one layer, but beneath it lies a kind of quiet philosophy, a reminder that our memories and our hopes are part of the same cosmic story told across billions of years. It's not just physics, it's something softer, something that feels like a whisper of who we are. Before we go on, uh, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, not just to explore the wonders of science, but also to help you drift off to sleep while we wander through these ideas together. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating. Well, always fascinating to see who's joining us from all around the world. So let's continue. Well, let's begin, I suppose, with something so familiar that we rarely stop to question it. Time. You know, we talk about time all the time, but what do we really mean when we say it? Is it just the ticking of a clock on the wall, or is it something deeper, something stranger? The physicists, well, they tell us that time is not just a number on your wristwatch. In classical physics, time was thought to be absolute, a kind of invisible stage on which the events of the universe unfold. Newton's world was a clockwork world, tick, 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 each moment following the next in an endless, reliable stream. But even Newton must have wondered sometimes, is it really so simple? And, well, when we turn to Einstein, the story grows richer. Einstein showed us that time and space are not separate things. No, they're woven together, stitched into a fabric called space-time. Imagine, if you will, that time is not a river flowing past you, but a direction, just like left or right, up or down, forward or back. In this new picture, every event in the universe has a set of coordinates, 3 for space and 1 for time. And this union of space and time is called Minkowski space-time, after the mathematician who first described it. Every heartbeat, every memory, every star exploding in the distant past, it all takes place at some point in this grand 4-dimensional landscape. Now, here's something curious. The notion of a proper time and an ideal clock. Proper time is, well, the time measured by a clock that moves along with you, ticking steadily as you journey from birth to old age. And the idea of an ideal clock, one that is unaffected by any forces, any imperfections, is perhaps a dream. In practice, every clock is subject to the universe, to gravity, to motion. Still, proper time is what keeps your story coherent as you move through space-time. So what does it mean to talk about the present, the past, the future in classical physics? Everyone everywhere would agree on what now means. But relativity tells a different story. If you are moving quickly, or if you are deep within a gravitational field, your now might not be the same as mine. The simultaneity, the idea that two events happen at the same time, is not absolute, but relative. It depends on your frame of reference, on your journey through the universe. And, well, here's another question. How do we know which events can affect which other events? Enter the light cone, a kind of map drawn through space-time. Imagine a flashbulb going off at a single point. The light from that flash expands outward, forming a cone-shaped region that grows as time passes. The inside of that cone is the future that can be reached from the flash. The outside is forever cut off, separated by the speed of light, the ultimate cosmic speed limit, and that is the strange heart of causality. Nothing, not even a thought, can travel faster than light. But the light cone is more than just a limit. It is the rule book for the universe's game. Anything inside your past light cone could, in principle, have affected you. Maybe a star exploded 1 billion years ago, sending its light towards your eyes tonight. Anything outside your light cone is, well, forever out of reach. That's the thing about the universe. It gives us this beautiful structure, a kind of scaffolding for every possible story. And in this structure, we can talk about something called the world line. Your world line is the path you trace out through space-time as you live your life. It's not just a trail of breadcrumbs. It's the story of every place you've been and every moment you've experienced. The world line of a photon, a particle of light, is different, of course. It travels along the very edge of the light cone, moving at the cosmic speed limit. But you and I, we move slower, winding our way through the fabric, one heartbeat at a time. Now, let's take a step back and look at the whole thing. Some physicists imagine the universe as a kind of block universe, where the past, the present, and the future all coexist, just as the entire map of a country exists, whether or not you are looking at a particular town. In this view, the now that feels so real to us is just a slice, a perspective, not the only reality. Well, it's a thought that can be unsettling. Is the future already written? Is the past truly gone? Or are we simply travelers moving from one part of the landscape to another? And that brings us, I suppose, to one of the most remarkable consequences of relativity. The speed of light is not just fast, it is the ultimate limit, the wall you cannot climb over. Nothing with mass can ever reach it. The closer you get, the harder the universe pushes back, as if space itself is saying no farther, not now. And that limit, well, it matters for time travel. Because, you see, if you could somehow break this rule, if you could step outside your light cone, you could, in principle, visit times and places that are forever sealed off. But the universe is careful with its rules. The speed of light is more than a number. It's the thread that keeps the tapestry of causality together. Remove it, and the story of the cosmos would unravel. Still, you might wonder, what if the rules could be bent, if not broken? What if there are cracks in the structure, little loopholes hidden in the equations? The physicists have looked and, well, sometimes the equations allow for strange things, curves that loop back in time, or regions where the fabric of space-time twists so much that you could, in theory, arrive before you leave. These are not just wild ideas, but mathematical possibilities that challenge our sense of what is real. And so the question is not just what is time, but also can we move through it in ways we do not expect? The answers are not easy, but they are deeply worth pursuing. The more we ask, the more the universe gives us, sometimes with a smile, sometimes with a riddle. Each fact about space-time is like a window, and each window opens onto a greater landscape, a universe that is, at every scale, both knowable and mysterious. It's not just science, you see. It's not just numbers and equations. It's a story, a human story, of curiosity and wonder, of the need to understand where we are, when we are, and perhaps, just perhaps, where else we might go. And, well, if you listen carefully, you'll hear the next questions calling, because it's not only the shape of time that matters, but how time itself can stretch and bend and change, how time can slow down for some and speed up for others. What would it mean to race alongside a beam of light, or to hover above the surface of a massive planet, feeling the seconds slip away differently? Well, that leads us onward into the next chapter of our journey, into a world where time is not just measured, but experienced, changed, dilated, where clocks disagree and the universe shows us that reality is richer than we ever dared imagine. So let's step forward slowly, curiously, and see what awaits us in the stretching and bending of time itself. And so, from the gentle curves of space-time, we drift forward into a landscape where time, well, is not just experienced, but stretched, twisted, made flexible by the very motion of things and by gravity itself. You see, Einstein's theory, the one we call relativity, it doesn't just describe a universe that sits still, it describes a universe that dances, where every movement and every mass can change the tempo of the cosmic clock. That's where the idea of time dilation comes in. It's not just a mathematical curiosity. It's something that happens, something you could experience if you were bold enough to travel fast enough, or if you were to, well, fall into the pull of a massive object. So let's imagine for a moment you're in a rocket ship, accelerating closer and closer to the speed of light. The faster you move, the slower your clock ticks, at least compared to the clocks of those you left behind. That's not just a thought experiment. It's a fundamental fact of our universe. We have seen it. And the universe has shown us this truth in experiment after experiment. Now, let's pause with that thought, because it's not just speed that warps time, it's gravity too. When you sit on the surface of the Earth, the planet's gravity pulls at you, and it also slows your clock just a little. If you could float high above the planet, where the pull is weaker, your clock would run a bit faster. It's not something you feel. We grow older at nearly the same pace as our friends, but the difference is there, written quietly into the ticking of the atoms themselves. And, well, this isn't just poetry, it's real physics. Scientists have flown atomic clocks aboard aeroplanes, comparing them to clocks left on the ground, and when the clocks are reunited, they no longer agree. The clocks in the sky have ticked ever so slightly differently from the clocks at home. The effect is tiny, but measurable, and it confirms what Einstein predicted more than a century ago. And if you want proof that this is not some faraway idea, but something that touches your daily life, look up, way up, to the satellites that orbit the Earth. The GPS system, the very one that guides your phone when you find your way home, it depends on clocks in those satellites. Those clocks must be corrected for both special and general relativistic effects, because in orbit, time runs at a different rate than on the surface. If we didn't make these corrections, GPS would become wildly inaccurate within hours. So, so every time you find your location with a tap on a screen, you are, well, whether you know it or not, relying on Einstein's insight into the nature of time. There is a certain beauty in knowing that the cosmos honors these rules and that we can witness them so clearly. And, well, there is more. Inside the laboratories where scientists speed up particles and accelerators, those enormous rings buried beneath the Earth, something wondrous happens. Take the muon, a particle born in the upper atmosphere, living for just microseconds in its own frame. When we watch these muons from Earth, their lifetimes are stretched, elongated by their near-light speed. They reach the ground not because they live longer, but because time for them is different, slower. The same is true in our accelerators. The faster the particles, the longer they seem to live. Time bends for them, as it would for you, if you could ride alongside. And, well, let's return to the twin paradox. A story that tickles the imagination. Imagine two twins. One stays at home, the other travels at great speed into space and then returns. The travelling twin finds that less time has passed for them than for the one who stayed behind. It's not magic, and it's not an illusion. It's a direct physical result of how the universe treats motion and time. The two twins compare their watches, and the universe delivers its quiet verdict. Time is not the same for everyone, but perhaps it helps to see this in the language of light cones. Every traveller, every event carries its own light cone, its own set of possible futures and pasts. As you move, as you accelerate, your cone tilts and changes. The relationships between events, what can cause what comes before and after, become subtly altered. And it's this shifting, this flexibility, that lets us even imagine journeys to the future. So the strangest thing of all may be this: going forward in time, traveling to the future, is not just possible, it's unavoidable. Every one of us is a time traveler, carried forward by the flow of existence. But if you move quickly enough, or if you live in a place where gravity bends space-time most strongly, you can travel further, faster, relative to everyone else. There are astronauts aboard the International Space Station who age just a tiny bit less than those of us here on the ground, simply because they are both moving quickly and orbiting above much of Earth's gravity. And in particle accelerators, we have made future travelers of our own, sending particles speeding around in circles, their lives stretched, their clocks slowed, all because of how they move through space-time. That is the heart of the relativistic future. It's not only possible, it's been measured, recorded, and tested again and again. Now, as we turn our gaze to even greater speeds, to even deeper gravitational wells, to black holes, to neutron stars, the differences become more dramatic, almost surreal. Near the event horizon of a black hole, time for an outside observer seems to slow to a crawl. A clock falling toward the horizon would, in theory, appear to almost stop, frozen by the intensity of gravity. But for the traveller, time would march on, undisturbed. That's the thing. What feels normal to you can look impossibly strange to someone else, watching from far away. The universe, then, is not a single story but many, woven together by each traveller's path, each clock's steady beat, each cone of light fanning out into the darkness. The rules are clear, but their implications, well, they are breathtaking. Relativity does not just explain the world, it transforms it. And um, in this transformation, we find paradoxes that are not true contradictions, but windows into a reality that is richer and more generous than our common sense might suggest. You see, the twin paradox is only a paradox if you expect time to be universal, the same for all. But in our universe, time is local, stitched to your own journey. And this is not some flaw in our reasoning, but a gift, a deeper way of understanding what it means to exist at all. There are experiments, oh, so many experiments where these ideas have been tested. The Hafele-Keating experiment, flying atomic clocks eastward and westward around the world, showed that both speed and gravity play their roles, just as the theory demands. The muons falling from the sky, created in the upper atmosphere by cosmic rays, they reach the ground in numbers that can only be explained if their time has been stretched by their speed. The GPS satellites, ticking quietly above our heads, must account for both effects, or we would lose our way. Each of these is a story, a proof, a gentle nudge from the universe saying, yes, this is how things are. And yet, even as we accept these facts, there is something deeply mysterious about it all. Why does the universe work this way? Why should time, so steady and reliable in our daily lives, become so flexible under the right conditions? And if traveling into the future is possible, if time is a road that can be stretched and twisted, what does that say about causality, about the nature of memory and hope? Is the future already there, waiting for us, or do we carve it out with every step? And well, perhaps you're starting to sense the outlines of the next great question. What does all this mean for cause and effect? If time can be bent, if clocks can disagree, then what of the web of relationships that holds the world together? Can we send a signal faster than light? Or is there something in the structure of space-time that forbids it, that protects causality itself? So we move forward slowly, thoughtfully, with a sense of awe into the next chapter. There we'll explore the shapes of causality, the boundaries of the light cone, the strange and beautiful structures that tell us not just where and when we are, but what can and cannot happen, what can touch us from the past, and what is forever out of reach. The journey is just beginning. And so, as we stand at the edge of what seems possible, let's take a deeper breath. Because, well, if relativity tells us that time bends and flexes, then causality, that gentle thread linking one moment to the next, is the loom that holds the whole tapestry together. We need it. We need causality to make sense of anything at all, that this follows from that actions have consequences, that our choices, however small, echo into tomorrow. But causality is not just a philosophical idea. It's built quite literally into the geometry of space-time. Imagine, if you will, that every event, each moment, each flicker of a thought or a star's explosion can be mapped not only by where and when it happens, but also by its possible connections to other events. It's not just a point on a graph. It's a node in a vast web, each thread defined by whether light, or anything at all, could connect those events. And, well, this is where the light cone returns to center stage. A light cone isn't just a diagram, it's the ultimate traffic law of the universe. When something happens right here, right now, its influence can only ever spread outward at the speed of light. Not slower, not faster. That's not just a technicality, it's the very foundation for cause and effect. Imagine, again, a stone dropped in a perfectly still pond. The ripples move outward, never instantaneously, always with a limit. And, well, the universe is a much vaster pond, but the same principle holds. Inside the future light cone, effects can spread. Outside, they simply can't reach. So there is always a boundary, a limit to what any event can touch and be touched by. And, and that leads us to something quietly profound. The classification of event separations. Two events in space-time can be time-like separated, space-like separated, or light-like separated. If you and I stand still a few feet apart, and then I walk over to shake your hand, that's a time-like separation. One event could, in principle, influence the other. But if we're on opposite sides of a galaxy, and we both blink at exactly the same moment, there's no way for a signal to travel between us fast enough. That's a space-like separation. Our nows are disconnected. And, well, when something happens exactly along the path light would take, that's a light-like or null separation, the boundary between possible influence and impossibility. What's so striking is that these distinctions aren't absolute. They depend on your frame of reference, your state of motion. That means for two observers moving differently, the sequence of two events, what comes first and what comes after, can flip. Simultaneity, as we said before, is relative. In one frame, one event is the cause. In another, it's the effect. And if you look at the equations, you'll see that only events inside each other's light cones are always in the same order for everyone. Outside the universe allows for, well, a certain kind of ambiguity. So this is why in relativity we must be careful. Not every before leads to an after for all observers. The order of things is protected only where cause can really reach effect. That is, where there's a time-like or light-like separation. And this is not just mathematical abstraction. It's the reason why no signal can travel faster than light, why instant communication across vast stretches of space would break the universe's sense of order. If you could send a message outside your light cone, if you could somehow call your friend in the Andromeda galaxy instantly, you could create paradoxes. For some observers, you'd receive the reply before you even sent the message. Cause and effect would blur or even reverse. The universe, it seems, is deeply committed to making sure that doesn't happen. And, well, this prohibition against superluminal signals is not just a rule, it's a safeguard for reality itself. And you might ask, what if the rule is broken? What if something could travel faster than light? Here we run into the paradoxes that, well, trouble physicists late into the night. If information could travel arbitrarily fast, it could circle back into the sender's past. It could arrive before it was ever sent. You might, in principle, receive a warning not to post that embarrassing photo before you'd even taken it. It's amusing, but it's also deeply unsettling, because if effects can precede causes, the logic of the universe crumbles, stories unravel. So the prohibition against superluminal signals is more than just technical detail. It's the guardian of causality, of memory, of narrative. There's a curious twist here, though. Quantum mechanics, well, it muddies the water. In the quantum world, we encounter the famous no communication theorem. Entanglement, that spooky action at a distance, seems to suggest that particles can be correlated across any distance instantly. And yet, when you look closer, the universe is careful again. Yes, entangled particles share information, but no usable signal travels between them. The correlations cannot be used to send messages faster than light. The quantum world, with all its strangeness, still bends the knee to relativity's guardrails. And well, this brings us to the question of locality. Locality means that what happens here is only affected by things in its immediate vicinity, or, more precisely, by events inside its past light cone. It's not just a comfort, it's the bedrock of physical law. If actions at a distance could influence events with no mediation, no field, no light, no wave, then the predictability of physics would collapse. You'd live in a world where your decisions could be undone by distant happenings, instantaneously. Not just strange, but incoherent. Still, the quantum world teaches us humility. Non-local correlations are real, but not causal. The distinction is subtle, but essential. It's not just the presence of connections, but the impossibility of sending usable information that saves causality. The universe maintains the illusion of separation for a reason. But let's look now at another cornerstone energy conditions. In general relativity, energy is not just a number. It's a constraint, a binding thread that shapes space-time. The average energy condition is one such rule. It limits the ways you can bend the fabric of space-time, enforcing that certain averages of energy taken along certain paths must remain positive. Why does this matter? Because many of the wildest proposals for time travel or causality violation, wormholes, closed time-like curves, require negative energy in exotic forms. And the universe seems deeply reluctant to allow this. It's not just about what's allowed, it's about what's protected. The integrity of causality rests on these subtle mathematical foundations. And, well, perhaps this explains why traveling into the past is so much harder, so much stranger than traveling into the future. The future is open, a wide field. We all move toward it, inevitably. The past is closed, tightly bound by the rules of causality. Every mechanism that would let you step backward seems, on inspection, to unravel or to require conditions that the universe so far refuses to provide. It's not a matter of technical difficulty, it's a matter of logical structure. The web of causality resists being torn. So let's take a step back and look at the big picture. The universe is not just a place, but a story written in the language of events, linked by the logic of causality. Each light cone, each separation, is a line in that story. And as we move through it, as we wonder about paradoxes and possibilities, we're always, in some way, negotiating with the rules that make stories possible at all. There is something quietly humbling about this, to realize that our sense of before and after, of cause and effect, is not just an accident, but a necessary part of how reality holds together. And but when we imagine breaking those rules, we're not just inventing new stories, we're testing the boundaries of sense itself. But, of course, there's more to causality than the forbidding of paradox. There are deep, beautiful connections with the way information and energy move through the universe. The no signaling principle in quantum theory, for example, is a cousin to relativity's ban on superluminal communication. And it ensures that even in a world where outcomes are not determined until the last moment, there's still a kind of order, a boundary between what can and cannot be known, what can and cannot be changed. This touches on the famous information paradox, where violations of causality could, in principle, lead to paradoxes about knowledge itself. If you could send information into your own past, you could learn things before they happened, create closed loops of knowledge with no true origin. It's not just confusing, it's destabilizing. The laws of physics seem built to prevent this, preserving not only the structure of events, but the very possibility of knowing anything at all. And And in the play between causality and information, we see why the universe must sometimes be non-local, but never a causal. Correlations can stretch across space, but messages, influences, real causes are always bound by the light cone. The universe is subtle. It flirts with the edge of paradox, but never falls in. It's not then just that the speed of light is fast. It's that the speed of light is a limit on reality. It's not just a technical speed bump. It's the defining edge between what is possible and what is fantasy. The speed of light is the do not cross tape at the scene of the cosmic play. And everything that happens because that boundary is respected. And so when physicists dream about bending the rules, about finding ways around causality, they always find the universe pushing back. The conditions required negative energies, exotic topologies, remain stubbornly out of reach, more at home in equations than in experiments. The universe, it seems, is more conservative than our imaginations. But still, there's a kind of poetry here, the poetry of connection, the poetry of limitation. We can reach, but not everywhere. We can know, but not everything. And perhaps that's what makes reality feel so real, so precious. It's the limits, the boundaries that give meaning to our choices, our hopes, our regrets. And as we press our hands against the window of the present, looking into the past and the future, we are always held gently but firmly within the lattice work of causality. The light cones that shape our stories, the energy conditions that keep the fabric taut, the impossibility of signals outrunning the cosmos itself, all these are, in a sense, the laws that make life possible at all. So the journey continues deeper into the paradoxes that haunt our dreams of time travel. Because, you see, as soon as you let your mind wander into the past, you find yourself entangled in contradictions, grandfather paradoxes, causal loops, self-negating actions that seem to dance on the edge of logic itself. The question isn't just can we, but what would happen if we did? And as the story of causality draws to a close for now, the door opens onto a hall of mirrors, a place where, if we could travel back, we would risk unmaking ourselves, or perhaps the universe itself. The logic is relentless, the questions profound. The fabric of causality holds, but only just. And beyond that, the landscape grows even stranger. The paradoxes await, calling us to step beyond the familiar, to test the limits, to ask not just what is allowed, but what can survive the tension between freedom and fate, between the past that binds us and the future that calls. So, well, with a sense of wonder and, yes, a bit of caution, let's take that next step into the realm of paradoxes, where time loops and self-defeating actions challenge the very heart of sense. The story of time travel is just beginning to unfold. And so, as we peer into the twilight between sense and paradox, the landscape shifts. It grows stranger, richer, more dangerous, like stepping through the looking glass into a place where the laws of causality, so steady, so reliable, begin to fray. You see, time travel to the past, at least in our imaginations, is not just an adventure. It is a test of logic, of identity, of the very fabric that makes stories and memories possible. And as we wander deeper, we find ourselves surrounded by paradoxes, those curious knots in the thread of time that seem to tug against the universe itself. The first, and perhaps the most famous, is the grandfather paradox. Well, it's a thought experiment, yes, but also a kind of riddle, a way of poking the boundaries of what is real. Imagine, for a moment, you build a machine, step inside, and travel back to a time before your grandfather met your grandmother. Suppose you interfere. Suppose, uh, through some accident or intention, your grandfather does not survive. What then becomes of you? You would never be born, yet you are there, acting in the past. That, that is the paradox. The cause, which is your birth, is undone by the effect, which is your own action. It's not just a puzzle, it's a wound in the logic of the world. How can something exist and not exist, be both actor and erased? The paradox is not just about murder or mischief. It is about the way the universe protects the consistency of stories, the way it guards the integrity of becoming. And it's not alone. There is the bootstrap paradox, or the information loop, which is, if anything, even more bewildering. Suppose you find, say, a book of mathematical theorems in your attic, and you bring it with you on a trip back in time. You hand it to a young mathematician who, in turn, grows up and writes that very book, which then finds its way back to your attic. The information has no origin, it is its own ancestor. Where, then, did the knowledge come from? Not just from you, not just from the mathematician, but from the loop itself. The story closes on itself, and the universe is left with an event that has no outside, no before. It is not just a violation of chronology, but a challenge to the very idea of causality as a chain. And well, then comes the Polchinski paradox, which dresses the bootstrap in the clothing of physics. Imagine a billiard ball rolling toward a time machine, say a wormhole that leads back into the past. If the ball emerges from the other side, and collides with its younger self in just the right way to prevent itself from ever entering, what happens? Does the collision stop the journey? If so, the ball never entered, so it could never have emerged to interfere. If it does not interfere, it does enter, then the loop repeats. The logic circles back again and again, always hungry for a consistent resolution, always chasing its own tail. These are not just mind games, they are blueprints for the problems the universe must solve, if time travel to the past is possible at all. And the human mind cannot resist extending these paradoxes to the realm of ethics, of history, of responsibility. The so-called Hitler paradox. What if you could go back and stop a tragedy, save millions, rewrite the past? Would you be allowed? Would the universe protect its own history, somehow preventing you from succeeding? Or would you find yourself caught in the machinery of unintended consequences? The question is not just can we, but should we? And what would it mean to live in a world where history is pliable? Not just a scientific puzzle, but a moral one, a place where the laws of physics meet the shadows of guilt and choice. So we arrive at the paradox of free will. If you travel to the past, can you act freely, or is everything you do already woven into the fabric of history waiting for you? Are you a participant or just an observer, playing out a script you cannot change? And if the universe demands consistency, perhaps it will arrange things so that you always fail to change the crucial events. Or perhaps free will is a deeper mystery than we have guessed, tangled up in the possibility of time loops, in the question of whether the future can ever shape the past. And, well, when we think about paradoxes, we must not forget the observer, the person who remembers, records, and tries to make sense of what happens. If time travel allows the past to be changed, what becomes of memory, of record, of truth? Suppose you witness a change, see the world shift around you. Does your memory survive? Do you remember two histories, or only the new one? Or is memory rewritten as if the old world never was? That is the paradox of observation. The universe must decide not just what happened, but what is remembered, what is real for those who live through the change. And chance itself enters the labyrinth. Imagine betting on the outcome of an event, then traveling back to influence the odds. If you win the lottery, then go back and change the numbers. Who wins? Can the universe tolerate such loops of fortune and misfortune, or will it snap like an overstretched string? The paradoxes multiply, each one a test of the strength of causality, of the resilience of reason, and the paradox of duplication arises if you travel to the past and encounter yourself, or even create another version of yourself. What then? Are you both the same person? Does your very existence become an overlapping circle, a Venn diagram of identity? These are not just questions of science, but of the soul, of what it means to be you when the line between past and present is blurred. But even the matter of energy conservation, the most basic law of physics, feels the strain. If an object loops through time, appearing more than once, does the total energy in the universe increase? Does the universe notice the extra mass, the extra heat, and rebel? Each loop, each return, is a challenge to the balance that keeps the stars burning and the world intact. And, well, at the tiniest scales, chaos lurks. Even the smallest nudge, the tiniest interference with the past, can ripple outward, breaking the symmetry, unraveling the loop. The universe is not always kind to repetition. Sometimes it only takes a whisper, a breath, to bring the whole fragile structure crashing down. So why do we keep circling these paradoxes? Perhaps it's because in them we glimpse both our limitations and our possibilities. The paradoxes are like stress tests for the architecture of reality, pushing against the doors and windows to see what will bend, what will break, and what will hold. They are not just obstacles, they are clues. If the universe cannot tolerate them, it will find ways subtle or dramatic to prevent them from happening. If it can tolerate them, well, we are left with a stranger, more circular kind of reality. Some philosophers suggest that paradoxes point to new laws, as yet undiscovered rules, that resolve the contradictions, close the loops. Others argue that paradoxes reveal the boundaries of our imagination, not the boundaries of the world. But whatever the answer, the paradoxes of time travel are invitations to think more deeply, to imagine more boldly, to let the mind wander down paths where reason and wonder meet. And as we move through these mazes, perhaps it is worth asking, what is it we hope to find? Is it mastery over time, the power to undo regret, to reclaim lost chances? Or is it, instead, the hope that the world makes sense, that the story of existence has a logic even when it loops back on itself? In every paradox, there is a lesson. The grandfather paradox teaches us about the fragility of origins. The bootstrap paradox warns us about the dangers of self-reference, of knowledge with no source. The Polchinski paradox shows us that even the simplest objects can tangle themselves in time, given the chance. The paradoxes of free will and observation remind us that consciousness, memory, and identity are perhaps even stranger than physics itself. And as we reach the far edge of the labyrinth, we find ourselves standing at the threshold of yet another question. If the universe resists paradox, how does it do it? What rules, what mechanisms, what hidden laws stand between us and the unraveling of reason? Do timelines branch and split so that every choice is played out somewhere? Does the universe enforce consistency with an iron hand, allowing only those actions that preserve its coherence? Or are there, hidden in the mathematics, principles that prevent the loops from ever closing? Well, these are not just speculations. They are the seeds of new science, principles like the Novikov self-consistency conjecture, of the many worlds interpretation, of quantum conditions and global constraints that may keep the past and future in delicate balance. And, well, as we step forward, we will see that for every paradox, there is a possible resolution, a rule, a loophole, or a deeper understanding that allows the story to go on. So let's carry this sense of wonder and perhaps a little humility as we cross into the next landscape, a place where the universe itself offers solutions, where logic and mathematics step in to heal the wounds that paradoxes reveal. The next chapter, then, is not just about the problems, but the ways the universe might, just might, tie up its own loose ends. And so, as we leave behind the hall of paradoxes, those haunting, beautiful riddles about time and cause and choice, we find ourselves standing at another threshold. The air here is thick with questions, but also maybe with the promise of answers. Because, you see, every paradox is not just a problem, it's also an invitation for the universe to reply, to offer a mechanism, a law, a twist of logic or mathematics that gently untangles the knots we've tied. And that's where this next landscape begins, with the search for ways the universe might heal itself, for rules and principles that keep the story of time and the story of us from collapsing under the weight of contradiction. So, well, perhaps the most famous of these ideas is the Novikov self-consistency principle, named for the Russian physicist Igor Novikov. It's a kind of cosmic safeguard, a rule that says, if time travel to the past is possible, then only those actions that are self-consistent can actually happen. The universe, in this view, is not so much a chessboard as a game of dominoes, where every piece must fit with the rest. If you travel to the past, you can do anything you like, so long as your actions do not create a paradox. You can visit your grandfather, you can talk to him, even influence him in subtle ways. But if your presence would create a contradiction, like erasing your own birth, then something, somehow, will always prevent it. The gun jams, the bus is missed, the crucial moment slips through your fingers. It's not fate, not magic, but the logic of consistency, rippling backwards and forwards through time, closing the loop without breaking the story. And there's something strangely comforting about this. The universe, in a sense, takes care of itself. There are still loops, still echoes and influences that spiral through time, but they always resolve. The past is safe, not because we are powerless, but because reality is robust. And this principle is more than just a clever idea. It's built into the mathematics of certain solutions to Einstein's equations. In some space-times, the laws of physics, when allowed to play out over and over, converge on outcomes that are always self-consistent, even when time loops are present. But, well, not everyone is satisfied with that. Because, you see, if self-consistency is the only rule, it feels a little like the universe is cheating, denying us our choices. That's where another great idea comes in, the many worlds interpretation, or, more specifically, the Everett branchings. In this view, every time a paradox threatens, the universe doesn't slam the door shut, it opens another. If you go back in time and do something that would change history, save your grandfather, rewrite the past, you don't destroy the present you came from. Instead, you create a new branch, a new timeline, a new world that grows alongside the old. The old history and the new one coexist, forever diverging, forever out of reach. The universe becomes a garden of forking paths, a tree whose branches multiply with every choice, every action, every journey through time. And there's a wildness here, a sense of infinite possibility. No longer is history a single thread, fragile and easily broken. It is a vast tapestry, endlessly expanding, where every contradiction is resolved not by prevention, but by multiplication. You don't erase yourself, you simply move to a world where you never existed. The price of paradox is paid by the splitting of reality itself. That, well, that is both exhilarating and a little overwhelming. Now, some physicists have tried to take these ideas and bind them even tighter. They speak of global boundary conditions, a kind of contract that the whole universe must sign, setting the terms for what's allowed and what's not just locally, but everywhere and every when. The universe, under these rules, is not free to do whatever it likes in one corner while breaking the story somewhere else. Instead, everything is coordinated. The initial conditions, the final outcomes, the entire history of space-time are woven together by hidden constraints. If you want to create a time loop, the conditions must be just right, not just at the moment you step into the past, but at every moment, past and future, that your actions touch. And, this idea of boundary conditions is both beautiful and daunting. It suggests a kind of cosmic harmony, a way the universe ensures that all its stories add up, no matter how tangled they become. It's not just about avoiding paradox, but about the deep structure of reality, the way everything fits together in a pattern too vast for any single observer to see. Of course, sometimes the universe is not so strict. There are solutions where probabilities come into play, where not everything is decided in advance, but some outcomes are simply more likely than others. Conditional probabilities, selective histories, self-sorting events. In some interpretations, the universe chooses the self-consistent path, not by banning all others, but by assigning them vanishingly small probabilities. Paradoxes aren't forbidden, exactly. They're just unlikely, fading out of existence as the logic of the universe asserts itself. That's the thing. The universe, it seems, prefers to heal itself gently with probabilities and adjustments, not always with brute force. And as we wander deeper into the mathematics, the language grows stranger still. Some physicists have proposed models like the Deutsch closed time-like curve, CTC, where information or objects loop back in time, but always in a way that arrives at a fixed point. In these models, whatever enters the loop must emerge in a state that is fully consistent with itself and the loop's history. The mathematics is subtle, and, the solutions are sometimes counterintuitive. But the essence is clear. The universe demands a kind of self-consistency, whether by adjusting the input, the output, or the path in between. Now, you might wonder about the practical side, the energy, the stuff of the world that makes these loops possible or impossible. Here, too, the universe seems to have rules. Many of the wildest time travel scenarios require negative energy, exotic matter, quantum fields, bent in ways that seem almost impossible. The classic energy conditions of general relativity act as a kind of safeguard. If you want to open a time loop, you need to pay a price that so far seems beyond our reach. The universe doesn't slam the door exactly, but it does set the bar high. But there are, well, loopholes. Quantum mechanics is full of windows, tiny openings where uncertainty, decoherence, and entanglement offer ways for paradoxes to soften, for contradictions to blur rather than shatter. Decoherence, for example, is the process by which quantum possibilities collapse into classical reality. It's not magic, but it is mysterious. In some models, it allows for histories to branch, for contradictions to fade out instead of exploding. The universe is clever. It sometimes prefers ambiguity over absolute prohibition. And what about the changes themselves, the acts that would rewrite the past, if only we could? Some physicists argue that even if such changes could occur, they would always be unobservable, hidden behind the veil of quantum uncertainty. You might believe you had changed the past, but the universe would make sure you could never prove it, never send a signal or a message that would reveal the contradiction. The universe is not just robust, it's secretive, keeping its own consistency behind layers of unmeasurable difference. This leads, naturally, to the principle of information conservation, a deep rule that the sum of all knowledge, all signals, all possible outcomes must be preserved, even when time bends and loops. In quantum physics, this is almost a sacred law. Information cannot be created or destroyed, only transformed, only hidden, only entangled. If time travel were to threaten this balance, the universe would find ways to protect it, to encode the information in forms that defy contradiction. And then, well, we come at last to uncertainty. The uncertainty principle. The fuzziness at the heart of the quantum world is more than just a limit to measurement. It is a safeguard against the worst excesses of time travel paradoxes. When events are fundamentally unpredictable, when outcomes are blurred by probability and chance, the loops lose their sting. You can't trace a path so precise that you break the story. You can't draw a circle so sharp that the universe must snap. The uncertainty principle is a kind of soft shield, a way for reality to keep its balance when all else grows strange. So as we step back and look at the whole landscape, what do we see? A universe that is, in some ways, stricter than we imagined, but in other ways, more forgiving. Not just a jailer locking the doors against paradox, but a gardener pruning, shaping, coaxing reality into self-consistent forms. Every paradox is a test, every test invites a solution, and every solution is perhaps a deeper invitation to look for the hidden order, the rules that bind time and story together. The Novikov principle closes the loop gently. The many worlds interpretation opens up new universes. Boundary conditions tie the world together in a silent contract. Probabilities and decoherence soften the edges. Conservation of information keeps the balance. Uncertainty ensures that, even at its wildest, the universe never quite loses the thread. And as we turn from these mechanisms, we find ourselves looking toward even stranger lands, the realm of quantum physics, where time itself grows slippery, and where the rules we thought we knew must be tested all over again. So, let's carry forward this sense of awe and perhaps, well, a kind of gratitude. The universe, for all its complexity, for all its paradoxes, is always finding ways to hold itself together. And as we cross this next threshold, we enter a place where the quantum and the cosmic collide, where time is no longer simply a line or a loop, but a shimmering possibility waiting to be explored. The journey, as always, continues. And so, as we drift from the edge of paradox into the heart of the quantum world, we find the landscape changing beneath our feet. The ground grows uncertain, shimmering with possibilities, as if the rules that seemed so solid only a moment ago are now written in fog. That's what quantum physics does, you see. It's not just a theory of the very small, it's a theory of the very strange, where cause and effect, time and measurement, all become questions without easy answers. And, well, perhaps nowhere is this more obvious than in the idea of delayed choice. Imagine, for a moment, that you are performing a classic experiment with light sending photons, one by one, through a pair of slits, and watching the pattern that forms on a distant screen. This is the double slit experiment, the one that's haunted physics for a century. But now, imagine you wait until after the photon has already passed the slits, after the decision should have been made, and only then do you choose whether to measure which path it took or whether to let the interference pattern form. The outcome depends, not just on what happened, but on how you choose to observe it. It's as if the present reaches back and reshapes the past, as if the act of measurement pulls reality out of a cloud of what might have been. And this is not just a trick of language, it's an experiment that's been performed again and again. The results are clear. The boundary between cause and effect, between before and after, is not as rigid as we once thought. It's not just that quantum events are unpredictable. It's that the very framework of time becomes flexible. A kind of landscape we travel through, not a series of gates we must pass. Now, some have wondered if this means we can send signals backwards in time, change the past, rewrite causality. But here, the universe is subtle, drawing a line between correlation and communication. There are quantum protocols, experiments that seem, at first, to allow retrocausality, effects that ripple backwards from future measurements. But when you look closely, when you try to extract a message or a signal, the universe steps in and closes the loophole. The quantum world is slippery, but not lawless. It allows the appearance of reversed causality, but not the reality. No information, no message, no change can be sent faster than light or backwards in time. The rules hold, but they hold in a new, almost poetic way. And, well, this brings us to the Wigner's friend paradox, a thought experiment that stretches not just the fabric of time, but the fabric of observation itself. Imagine, if you will, that you are performing a quantum measurement inside a closed laboratory. Outside, another observer, Wigner waits to see what results you announce. For you, the outcome is real and definite. For Wigner, until the door opens, everything is still a probability, a wave function not yet collapsed. The story splits inside one reality, outside another. And if the rules of quantum mechanics are universal, then even observers are subject to uncertainty. The very act of observation, of witnessing the world, becomes tangled with the thing being observed. And this leads naturally to the idea of time reversal at the most fundamental level. In the equations of quantum physics, time often appears as just another variable, one that can be run forward or backward without changing the basic rules. The fundamental processes, scattering, superposition, entanglement, they work just as well in reverse. The arrow of time, the sense of before and after, is not built into the quantum world at the smallest scales. It's something that emerges later from the collapse of probabilities, from the turning of entropy, from the way the universe remembers its own history. But it's not just about the equations. There is something deeply mysterious about entanglement, about the way two particles, no matter how far apart, can share a kind of unity. a single wave function stretched across space. Entanglement does not send messages, but it does enforce correlations instantaneously, everywhere. It's not just that the universe is connected, it's that the rules of information are woven into the fabric of reality. And and while entanglement can't be used for faster than light signaling, it can set absolute limits on communication, on what can and cannot be known, on what the world allows us to change. Now, well, if we try to measure time itself at the quantum scale, we run into new limits. Quantum clocks, clocks built from atoms, from spins, from the purest moments of change, are subject to uncertainty. The more precisely you try to measure the passage of time, the more the universe resists, smearing the results, blurring the ticks and tocks into a haze of probability. The Planck scale, the ultimate quantum boundary, sets a floor on how small, how sharp, how exact our measures of time can be. Time, at this scale, is not a river or a line, but a mist, a probability, a possibility, something we can only grasp for a moment before it slips away. And so it becomes clear that in the quantum world, time travel, paradox, even causality itself are not as simple as we once hoped. The universe plays by rules, but the rules are stranger than any story we could have written. The delay of choice, the blur of measurement, the puzzle of entanglement, these are not just curiosities, but the foundation of reality. But, as always, the story is not just about what we can do, but about what it means. When we ask whether the past can be changed, whether messages can be sent backwards, whether the future is set or still unfolding, we are really asking about the limits of knowledge, about the boundaries of experience, about the meaning of memory and hope. It's not just out there in the quantum fields and the equations. It's in here, in the way we think, the way we remember, the way we dream about tomorrow. The quantum world is perhaps a mirror, a place where the deepest questions about time and existence are reflected back at us, shimmering, unresolved. And as we move from the quantum to the cosmic, from uncertainty to the grandest scales, we find new puzzles, waiting black holes, wormholes, singularities, places where time itself bends and breaks, where the universe tests its own limits and invites us to imagine what might lie beyond. The journey, well, it is far from over. And so the story leads us from quantum strangeness out into the depths toward the dark hearts of the cosmos, toward places where even time can lose its grip. Because, well, if quantum physics invites us to question the nature of measurement and the flow of moments, then general relativity answers with a landscape sculpted by gravity so fierce, so utterly relentless, that space and time themselves become fluid and unstable. The journey is no longer just about the tick of a clock or the dance of particles, but about horizons, about tunnels through space-time, about the wild hope of time machines hiding among the stars. And let's begin with black holes. Not just any black hole, but a spinning one, the Kerr black hole. When you imagine a star collapsing under its own weight, what's left behind is not just a point, not just an empty shell, but a region of space-time so distorted that nothing, not even light, can escape. Yet when that star spins, as all real stars do, the black hole that forms is wrapped in layers. The outer shell is called the ergosphere, a region where space-time itself is dragged along, swirling like cream in coffee. It's not just a metaphor. In the ergosphere, nothing can stay still. The fabric of reality is pulled along by the whole spin. And Well, this dragging of space opens a door. It allows, at least in theory, for energy and even information to be extracted for paths that loop in on themselves in the most peculiar ways. And this leads us to one of the strangest ideas in all of physics, the wormhole. Einstein and Rosen, decades ago, wrote of a bridge, a shortcut, a tunnel connecting two distant points in space-time. Picture, for a moment, the universe as a sheet of paper. If you fold that sheet and poke a hole through, you connect two distant places in a single leap. That, in essence, is a wormhole. It's not just science fiction. It's a real solution to Einstein's equations, allowed by the mathematics, though perhaps not by the actual stuff of the universe. The trouble is, well, that keeping a wormhole open requires a kind of matter, so-called negative energy, that we've never seen, never touched. Ordinary matter tries to pinch the tunnel shut, but negative energy, if it exists, would hold it open, allow it to function as a bridge, maybe even a time machine. But negative energy is a tricky business. In quantum theory, there are fleeting hints, tiny pulses of negative energy in the vacuum, the whisper of virtual particles flickering into and out of being. But to hold a wormhole open for a traveller, or to allow a message to pass, you'd need a sustained, controllable supply. The universe, so far, keeps this secret well. It's not just a question of can we, but of is there any way at all that the cosmos will allow such a thing to endure. And even if you could construct a wormhole or harness a spinning black hole, stability becomes the next obstacle. Black holes, wormholes, any hypothetical bridge across time or space, they're all prey to radiation, to quantum fluctuations, to the relentless feedback of the universe's own energy. A wormhole could collapse in the blink of an eye, or worse, its very existence could create an avalanche of effects that destabilize it before anyone could cross. The closer you look, the more the equations warn you. Tread carefully, for the universe is not quick to allow shortcuts, not eager to grant safe passage between its most distant realms. But there's more. Every passage, every window through time and space, is bordered by a region where causality itself hangs in the balance. Near the mouth of a wormhole, the laws that keep cause and effect in order are stretched to their limits. What is before and what is after can become tangled, and the possibility of paradox returns, this time written not in logic puzzles, but in the mathematics of space-time curvature and event horizons. And, well, this brings us back to the concept of the causal window, the boundary within which information can flow freely, but beyond which paradoxes might sprout, wild and uncontained. Quantum back reaction enters the stage here as a kind of cosmic referee. Whenever energy or information tries to pass through a wormhole or hover near a black hole's horizon, the universe responds. Quantum fields ripple, particles appear and vanish, and sometimes the very act of trying to create a shortcut triggers feedback, like a microphone shrieking in a feedback loop, threatening to tear the passage apart. It's as if the universe is aware of its own boundaries and resists their violation with every tool it possesses. And yet, the most profound puzzle lies with black holes themselves. Stephen Hawking showed us that black holes are not, after all, entirely black. They radiate, they evaporate, slowly, leaking energy and perhaps information. The question of what happens to that information is one of the greatest riddles of modern physics. If a traveller, or even a single bit of information, falls into a black hole, is it lost forever? Or is it encoded somehow in the radiation that escapes in the quantum ripples left behind? The information paradox is more than just a technical glitch. It's a test of whether reality keeps its own books, whether time and memory can be truly erased. Well, attempts to answer this question have led to some of the most daring ideas in theoretical physics, holographic principles, complementarity, the suggestion that the universe, at its deepest level, is a kind of quantum computer, forever preserving every detail, every possibility, every echo, but no one knows for sure. The edge of a black hole is a boundary in more ways than one, a horizon for matter, for energy, for the knowability of the universe itself. And so we arrive at the practical challenge, even if the equations allow for time machines, wormholes, spinning black holes, singularities. Does the real universe permit their construction? Could a civilization, even in the far future, gather the energy, the precision, the understanding required to bend space-time to such an extent? Or are there hidden prohibitions built not into the mathematics, but into the grain of reality that render these dreams forever unreachable? The technical barriers are immense. The demands for stability, for negative energy, for control over quantum feedback, they rise like mountains, daunting and unforgiving. But perhaps what's most humbling is the sense that even the wildest ideas of time travel, of bridges through space and time, return us again to the old truths. The universe is both generous and strict. It offers hints, solutions on paper, whispers in mathematics, glimmers in quantum foam, but it guards its deepest secrets well. We are allowed to imagine, to calculate, to dream, and yet the doors may close, softly but firmly, whenever paradox, instability, or unpayable energy debts threaten the grand structure of reality. And, well, the more we ask, the more the universe replies in riddles. Each step deeper, each exploration of black holes, of wormholes, of cosmic bridges leads us not to final answers, but to new questions. What truly is possible? What is merely dream? Where do the boundaries of law, of energy, of time finally rest? And so the search continues, not just for bridges through space, but for ways to loop time itself, to fold the cosmos into paths that begin and end at the same moment. The next chapter opens with these questions about cosmic strings, about the engines of the impossible, about the secret doors that might, if we are bold or lucky or wise enough, reveal themselves in the structure of space-time. The story of time travel, of course, is never just about what we find, it's about what we are allowed to hope for, and about the courage it takes to ask the next question. And so, as we leave behind the shadow of black holes and the wild flickering mouths of wormholes, the universe opens up new paths, paths that at first glance seem even stranger, more ambitious. It's not just about falling into a cosmic abyss or threading a tunnel through the stars. No, now we're talking about weaving the fabric itself, bending, twisting, shaping space-time on colossal scales, hoping to find in the very geometry of the universe a new kind of time machine. The questions grow larger, and maybe, well, so does the hope. Picture, for a moment, the idea of a cosmic string. Not a string you can pluck with your finger, but a thread of pure energy, thinner than an atom, stretching across the universe like a scar left behind after a grand cosmic phase transition. Some physicists imagine these strings forming in the earliest moments after the Big Bang, when the universe itself was young, hot, and wild. These are not just relics, they are engines of geometry, able to warp space and time as they move, as they vibrate, as they loop. And If two cosmic strings were to pass by each other, or perhaps even loop together, the effect on space-time could, in theory, create a closed time-like, curve a path through space-time that returns to its starting point, a literal loop in time. But, well, the theory grows even richer. The mathematics shows that if you can get two such strings moving past each other at immense speeds, their gravitational fields would allow for shortcuts through time. The geodesics, the straight lines of space-time, would twist around the strings, forming circles in both space and time. The possibility is wild, but the equations do not forbid it outright. It's not just science fiction. It's there, hidden in the subtle folds of Einstein's general relativity. Now, if cosmic strings are the filaments of time, what about the warp drive, the famous Alcubierre drive, dreamed up in the 1990s? It's a solution to Einstein's equations, at least on paper, that envisions a bubble of space-time carrying a ship faster than light by expanding space behind it and contracting space ahead. You see, the ship doesn't move through space in the usual sense. Instead, space itself moves around the ship. It's not just a metaphor, it's a reimagining of what it means to travel at all. And inside this bubble, time could behave in bizarre ways, ticking differently for the traveller, bending in ways that ordinary intuition cannot grasp. Some solutions even hint that with clever construction, a warp bubble could create closed time-like curves, a literal machine for revisiting the past. But there's a catch, always a catch. To create these bubbles, or to keep a wormhole open, or to loop time around a cosmic string, you need negative energy. Not just a bit, but vast, unimaginable amounts. And, well, negative energy is not something we have in our pockets. The universe seems reluctant to provide it in the quantities required. Even in quantum physics, where the vacuum sometimes dips below zero, the total is always balanced. It's as if the cosmos itself is stingy, refusing to let anyone cheat at the game of reality. And so the dream of a warp drive or a cosmic time machine runs up against the wall of energy conditions. Physicists have found quantum inequalities, mathematical limits on how much negative energy can exist and for how long and in what configuration. The more you try to build a time machine, the harder the universe pushes back, insisting on balance, on order, on a harmony that resists all shortcuts. The proof is not absolute. There are loopholes, windows of possibility, but the weight of evidence is daunting. Each path forward becomes steeper, more technical, more demanding. Yet, the questions keep coming. If the universe is so careful, so reluctant, why do the equations still allow these possibilities? Is there a deeper law hiding beneath the mathematics that will one day shut the door for good? That's where the chronology protection conjecture comes in, a principle first proposed by Stephen Hawking that suggests the laws of physics themselves conspire to prevent the creation of time machines. Not by decree, but by subtle sabotage, quantum fields might explode with radiation near a would-be time loop, or space-time itself might become unstable, erasing the possibility before it ever takes shape. This isn't just pessimism, it's a sign of the universe's deep commitment to causality. The closer you get to creating a loop in time, the more the quantum and gravitational effects pile up, destabilizing your machine, making the dream ever more distant. It's not just a technical problem, it's a sign that the universe has a sense of story, a way of maintaining the difference between past and future, between cause and effect. But the story isn't over. There are still quantum questions, still corners of the mathematics where loopholes might remain. Some physicists ask whether, under certain circumstances, quantum effects could stabilize a time machine, or at least allow a fleeting window A, brief opening where a message or a particle or even a person might slip through, leaving a trace in the fabric of history. Others wonder about the so-called back reaction, the feedback between matter, energy, and space-time geometry. In some scenarios, the very act of trying to build a time machine triggers a runaway process, a flood of quantum effects that closes the loop, undoes the possibility, or even tears space-time apart. And, well, there's a beauty in the stubbornness of reality. The universe is not just a blank canvas for our dreams. It has structure, resistance, resilience. Each attempt to engineer a time loop is met with opposition, sometimes fierce, sometimes subtle, always present. But it is this resistance that gives meaning to the search, that makes every calculation, every experiment, every wild hope a test of understanding. It's not just about what's possible, but about what survives the test. The lessons learned in these explorations echo back into the heart of physics, teaching us about energy, about information, about the symmetry and asymmetry of the laws that govern everything we see and know. So as we weigh these bold designs, cosmic strings, warp bubbles, closed time curves, we must also ask what they teach us about the universe itself. Is reality open, always inviting us to push further, to imagine more? Or is it gently, persistently, always correcting, always restoring the balance, always insisting that the story must make sense, that cause must precede effect, and the conclusion, if there is one, is still open? The mathematics is dazzling, the imagination unbounded, but the evidence, so far, suggests that reality is more protective than permissive, more cautious than careless. Perhaps, someday, a new principle or a deeper understanding will emerge, revealing whether these dreams are truly forbidden or merely waiting for a bolder, wiser mind to find the key. But as we leave behind these cosmic engines and impossible architectures, the journey turns again. Now, we are called to reflect not just on the loops and shortcuts, but on the flow itself, on the direction of time, on the deep connection between entropy, memory, and the arrow that leads from past to future. The next chapter promises to be no less mysterious as we try to answer not just how time might loop, but why, in the end, it so stubbornly flows forward. And so, as we close the chapter on cosmic strings and warp drives those bold ideas for bending reality into loops and shortcuts, we find ourselves drawn back to a deeper, more familiar mystery. Why, in the end, does time always seem to flow in one direction? Why, when we look at the world around us, does the past sit quietly behind us while the future waits wide open and uncertain? Why do we remember yesterday but never tomorrow? Well, this is the puzzle of the arrow of time. And it cuts to the heart of everything: physics, memory, life itself. You see, at the foundation of this question lies the second law of thermodynamics, a law so fundamental, so universal, that it shapes every moment of our experience. The law says simply that entropy never decreases in a closed system. Or to put it another way, the disorder of the universe tends to increase. Things fall apart, they don't come together. That's why hot coffee cools, why ice melts, why life is a brief flare of order in a sea of chaos. The arrow of time is, at its root, the arrow of increasing entropy. But what does this really mean? Is the universe doomed to run down, to grow ever colder and more uniform? Or is entropy, perhaps, the secret that ties together physics and memory, cause and effect. You see, the second law is not just a rule about heat, it's a rule about information. The universe started somehow with incredibly low entropy, an extraordinary state of order at the beginning of time. Everything that's happened since, every star, every life, every story is a consequence of that original imbalance, that cosmic starting gun that set the arrow of time in motion. And this initial condition is a mystery all its own. Why was the early universe so smooth, so uniform, so packed with potential for change? Why wasn't it already in equilibrium, already spent? The boundary conditions at the Big Bang, this low entropy past, are, well, one of the great puzzles at the intersection of cosmology and thermodynamics. Some physicists suggest that the arrow of time and all the structure we see is a result of this singular, improbable beginning. Now, as time moves forward, entropy increases, not just out there in the universe, but in here, in our minds and memories. The psychological arrow of time is bound to the thermodynamic arrow. We remember the past because our brains, our records, our photographs all rely on the direction of increasing entropy. To form a memory is to create order, to carve out a tiny island of structure in a sea of noise. But each act of remembering also leaves a trace, a wake of increased disorder somewhere else. We grow older, clocks tick, stars burn out, the universe forgets as much as it remembers, and, well, the cosmological arrow of time points in the same direction. The universe expands, galaxies drift apart, the afterglow of the Big Bang grows colder and fainter. The story is not just about one arrow, but about the alignment of many: thermodynamic, psychological, cosmological, and even the radiative arrow, the reason why light spreads out from a source, not in from the distant future. All these arrows are manifestations of a single truth. The world is out of balance, always moving from order to chaos, from possibility to history. But why can't we reverse the film, watch the world run backward? The equations of fundamental physics, Newton, Maxwell, Schrödinger, even Einstein's relativity are time symmetric. They don't care which way the clock runs. If you filmed the motion of the planets or the dance of atoms and played it in reverse, the math would work just as well. It's only when you zoom out, when you look at the world as a whole, that the arrow asserts itself. So what enforces this irreversibility? One answer lies in decoherence, the process by which quantum possibilities, once entangled with the environment, lose their ability to interfere. It's not just that events happen, it's that history split, choices become facts, the present separates from the past. Decoherence links the microscopic reversibility of physics to the macroscopic irreversibility of life. Every quantum measurement, every interaction leaves a trail of entropy, a record that cannot be erased. And the mixing of states, the spreading of information, means that on large scales, the universe is fundamentally unpredictable in reverse. You can't unmix the cream from your coffee, can't uncollapse a quantum state, can't unburn a star. The arrow of time is a story about memory, about the impossibility of perfect reconstruction. We can simulate the past, we can model the possibilities, but the information is always incomplete, always blurred by entropy. Still, the mathematics holds surprises. The Poincaré recurrence theorem tells us that, given infinite time, a closed system will eventually return to a state arbitrarily close to its initial configuration. That is, if you wait long enough, the atoms in your room will, by pure chance, find themselves back in exactly the same arrangement they started. The odds are so vanishingly small that for anything larger than a few particles, the recurrence time is longer than the life of the universe itself. But it's a reminder the laws of physics do not forbid time running backward. They just make it extraordinarily, almost unimaginably unlikely. And, well, there's another way to think about time as an emergent phenomenon, something that rises out of the statistical behavior of many particles, many interactions, many histories. Effective time, as some physicists call it, is the story told by the universe as it moves out of equilibrium. It's not an absolute, but a pattern arising wherever there are boundaries, imbalances, gradients of energy and information. We experience the arrow not because the universe commands it, but because we are built on the edge of order and disorder. So, what does this mean for time travel, for the possibility of moving backward against the flow? If you could rewind the universe, reverse every interaction, erase every memory, you would still face the wall of entropy, the boundary between what can be simulated and what can be lived. To journey backward is not just to retrace steps, but to unmake the world, to erase the very conditions that make experience possible. And the implications for paradox are profound. The second law is a silent lawmaker, always present in every story of time travel, always resisting loops and reversals. Even if, in some corner of the equations, a time machine is allowed, entropy sets a trap. The longer and more complex the journey, the harder it is to keep the story straight, to avoid unraveling into chaos. The universe is a master of balance, but also of drift, always finding new ways to spread, to mix, to blur the line between what was and what could be. The universe began with low entropy, a near perfect order, and from that, all time flows. The arrow is not just a direction, it is the legacy of the beginning, the echo of the Big Bang, the cosmic drumbeat that keeps us moving forward, never back. Every galaxy, every atom, every thought is shaped by this drift from order to disorder, from creation to dissolution. But, well, there are always subtleties. Not every arrow is perfectly aligned. Psychological time can differ from cosmological time. Our memories can play tricks, histories can split, entropy can fluctuate, the boundaries of what's possible are not always clear. Quantum effects, decoherence, cosmic expansion all conspire to make the arrow robust, but also sometimes ambiguous. The universe is generous in its complexity, offering endless ways to think about time, entropy, and the direction of becoming. And as we try to sum up, it becomes clear the arrow of time is not just an abstract rule, not just a mathematical quirk. It is the shape of our lives, the condition of our experience, the guarantee that stories move forward, that memories have weight, that choices are possible. Without entropy, there would be no history, no evolution, no sense of self. So, as we ponder the great tapestry of time, the unbreakable flow from past to future, the cosmic push from order to chaos, we find ourselves, once again, standing at the edge of mystery. Because if the arrow is so strong, so universal, why do the laws of physics allow its reversal, even in principle? What is it about the boundary conditions, about the origin of the universe, that grants us the gift and the burden of the arrow? These questions lead naturally into the next realm, where information, computation, and the logic of causality itself become the battlegrounds for understanding time. The next chapter will take us into the world of computers and paradoxical algorithms, of information loops and the limits of what can be known or changed. The journey, as ever, continues as the arrow points onward. And so, as we follow the arrow of time through entropy, memory, and the relentless unfolding of the universe, we arrive at a landscape shaped not just by matter and energy, but by logic itself. Here, the terrain is made of information, bits and codes and questions about what can be computed, what can be known, and what, if anything, can be changed. You see, the universe is not just a physical object. It's also, in a profound way, a computer, a machine that processes information, step by step, moment by moment. And, well, when we bring time travel into this world of computation, the paradoxes and possibilities become even more intriguing. Let's begin with the Deutsch model of computation, with closed time-like curves. It's a bold idea. What if you could feed the output of a computer back into its own input, not just once, but through a loop in time itself? David Deutsch, in the late 20th century, proposed a way to imagine quantum computers enhanced by time travel. In this model, the computer sends a bit or a qubit through a closed time-like curve, a loop in space-time that lets information travel back to its earlier self. The requirements are strict. Whatever information emerges from the loop must be consistent with what was sent in. There can be no paradox, no contradiction, no information from nowhere. The mathematics of the Deutsch CTC demands a fixed point, a self-consistent solution, just as the Novikov principle demands self-consistency in physical time loops. And what does this mean for the power of computation? The implications are extraordinary. In the presence of a closed time-like curve, certain problems normally considered intractable, even for quantum computers, can, at least in theory, be solved almost instantly. These include problems in the class no problem, the infamous set of computational tasks that are hard to solve but easy to check. The computer can, so to speak, guess a solution, check its own guess, and send the answer back to itself, looping until a consistent answer is found. It's not just faster, it's a leap beyond the usual hierarchy of computation, a glimpse of what might be possible if time itself were a resource. But this leads us right into new paradoxes, algorithmic loops that seem to undermine the very logic they are built on. Imagine a self-affirming loop where the computer receives an answer from its future self, checks it, and then sends it back. If the answer is correct, the loop is stable. But if there is no answer, or multiple answers, or an answer that depends on itself in an infinite regress, the loop threatens to break or to become meaningless. These are the algorithmic paradoxes of time travel, loops that close on themselves, computations that create their own questions as well as their own answers. And well, there are physical limits here too. The universe is not just a mathematician's playground. It is a world of particles and fields and causality. Even if the mathematics of CTCs allows for supercomputation, the laws of physics may not. There are boundaries both in the energy required to build a time machine and in the nature of information itself. Not every mathematical solution corresponds to a real process in the world. The no-signaling theorems, the energy conditions, the deep constraints of quantum mechanics all push back against the dream of a universe where every computation, every paradox can be resolved by a loop in time. There's something humbling about this. The story of time travel in computation is a story about the limits of knowledge, the boundaries of what can be predicted or controlled. It's not just about making computers faster. It's about the fundamental nature of causality, about whether information can escape its own history, about whether there are facts that cannot be changed. no matter how clever the algorithm. And, well, as we look closer, we see that even in the presence of time loops, there are strict rules about what can be communicated. The no signaling principle is not just a feature of quantum theory, it is a deep law of nature. Even when quantum entanglement or closed time-like curves are brought into play, you cannot send messages into the past in a way that violates causality. Any attempt to do so, any signal that would create a paradox or an inconsistency is quietly filtered out by the mathematics, by the logic of the system, by the structure of the universe itself. So the lesson is clear. In the world of information, as in the world of physics, the story is about constraints, not just possibilities. The universe allows many paths, many computations, but always under the guidance of rules that protect the consistency of time, the integrity of memory, the coherence of history. It's not just about computers, either. These ideas have echoes in every science, every question about the limits of knowledge and the nature of reality. The logic of time travel is the logic of causality, the logic of stories. It tells us that not every question can be answered, not every loop can be closed, not every problem can be solved by brute force or by cleverness alone. And as we ponder these algorithmic mysteries, the boundaries between information and material reality blur. Computation is physical. After all, every bit must be stored, every calculation must be carried out in the world, subject to the same thermodynamic limits, the same quantum uncertainties, the same flow of entropy that shapes all of time. Well, as the story of time travel and computation draws on, we find ourselves returning to the central themes: balance, consistency, the impossibility of certain shortcuts. The lessons of quantum mechanics, of thermodynamics, of relativity, all return, each with their own perspective on the possible and the impossible. And so the journey continues, now inviting us to look for time travel, not just in the realm of thought experiments or distant stars, but in the technologies and measurements of our daily lives. Because the next chapter will ask, what about real time travel, the kind we can witness, even if only by a hair's breadth? What can we learn from the clocks on satellites, from experiments in laboratories, from the light of ancient stars? The boundary between science fiction and science fact grows thinner, and the adventure presses on, always guided by the logic, the rhythm, the wonder of time. Well, as we follow the story deeper, it's tempting to imagine time travel as something that belongs only to fiction, or perhaps to the outer reaches of theory mathematical models, black holes, or quantum puzzles. But the truth is that time travel, at least in some humble form, is already happening, right here, right now, all around us. It's not just science fiction, it's a scientific fact woven into our technology, our measurements, even the way we look at the sky. And the more we pay attention, the more we realize that the universe itself has given us a laboratory for experiencing time's strangeness, not just as a dream, but as a measurable reality. You see, the first kind of real-time travel happens every time you move fast, every time you accelerate to a significant fraction of the speed of light. The effect is called time dilation. And it's not just theoretical. Astronauts aboard the International Space Station, circling the Earth at incredible speeds, age just a little bit less than those of us standing still on the ground. The difference is tiny, measured in milliseconds, but it's there, recorded, undeniable. We really do travel into the future, if only by a hair's breadth, whenever we ride a rocket or orbit the planet. And, well, the effect is even stronger if you move through stronger gravity. Near a massive body like the surface of the Earth, or near a neutron star, clocks run slower. This is gravitational time dilation, a direct consequence of Einstein's theory of general relativity. If you lived your whole life at the top of a mountain, your heart would beat just a little faster. Your life would be ever so slightly longer than if you lived at sea level. The difference is so small that we don't notice it in our daily lives, but our technology depends on it. Every GPS satellite orbits high above the Earth, where gravity is weaker and speed is higher. The atomic clocks on these satellites tick differently than those on the ground. And if we didn't correct for both effects, speed and gravity, our maps would drift by kilometers every day. It's not just a technical detail. It's the universe at work, bending time to its will, even in the palm of your hand. And, there's more. Scientists have flown atomic clocks on airplanes, carrying them around the world and comparing them with clocks that stayed put. When the clocks reunite, they disagree not by much, but by just as much as relativity predicts. It's a reminder that, at its heart, the universe is a place where every path through space-time is unique. Every journey carves its own tempo, its own measure of the hours. Now, let's think a bit more deeply about these clocks. If you try to synchronize two clocks on Earth, one at sea, level 1 at altitude, you'll find they slip out of phase over time. The effect is tiny, but in experiments where absolute precision matters, it's essential. Particle accelerators, for example, keep particles whirling close to the speed of light for microseconds or less. But in that fleeting instant, the particles age less than the world outside. The lifetime of the muon, a heavy cousin of the electron, is stretched by its speed, allowing it to reach the Earth's surface from the upper atmosphere. If it weren't for relativistic time dilation, those muons would vanish long before they arrived. So real time travel is not just possible, it's routine. The universe grants it to us every day, in every experiment, in every satellite, in every tick of every clock that moves or feels the tug of gravity. And perhaps the most poetic example of all is in astronomy itself. When we look out into the night sky, we are always seeing the past light from stars that began its journey millions, even billions of years ago. The cosmic microwave background, that faint glow left from the Big Bang, is not just a relic, it's a message from a universe as it once was, billions of years before our time. The further we look, the further back in time we travel. Our telescopes are, in a sense, time machines, windows into the past, not just metaphorically, but literally. And in the ground beneath our feet, fossils, rock layers, and even ancient tree rings are time capsules, records of lives, climates, and catastrophes long gone. Every stratum of Earth, every glimmer of radioactive decay, every preserved artifact is a marker on the road of history, a reminder that time's flow can be measured, reconstructed, even, in a way, visited through the imagination and the tools of science. And, as our technology grows, we become ever better at preserving, reconstructing, and simulating the past. Digital archives, vast databases, artificial intelligence trained on the memories of billions become a new kind of time travel, one not limited by the speed of light, but by our ability to encode, store, and retrieve information. Simulations can recreate the world as it once was, down to the motion of atoms and the flicker of ancient skies. The past becomes, if not accessible, at least imaginable in unprecedented detail. But there's more, a subtler, quieter form of time travel that happens in every act of conservation, every effort to preserve the stories, the images, the songs of earlier generations. Libraries, archives, museums, even the code that protects our digital lives, all are efforts to cheat time, to hold on to the past, to build bridges across the river of forgetting. And uh, in a real sense, every effort to encode and protect information, whether through cryptography, redundancy, or preservation, is a battle against entropy, a refusal to let the arrow of time erase what matters most. So, so we grow older, clocks tick, technology advances, and still the search for meaning in time travel continues. The journey is not just about paradoxes or equations. It is about living in a universe where every moment is both a point in a story and a window into eternity. Whether it's an astronaut aging more slowly, a satellite keeping perfect time, a telescope looking into the deep past, or a fossil holding the memory of a vanished world, time travel is everywhere if we only know how to look. And perhaps this is the most important lesson. Time travel in the real world is not always about jumping centuries in an instant. Sometimes it's about seeing the flow, understanding the structure, preserving the record, and learning how to read the messages that the universe has left for us on land, in sky, in data, in memory. Well, as we reach the end of these everyday miracles, the journey isn't over. The final chapter beckons, a chapter about ethics, about law, about the place of time travel in our dreams and our cultures. What do we owe to the past? How should we face the future? When technology lets us touch or imagine times that aren't our own, what responsibilities do we carry? So, let's step forward one last time and see what lessons the future and the past have left for us. And so, as we stand at the edge of what science can show us, astronauts aging slower, satellites ticking away, fossils speaking from epochs past, there's a deeper river that flows beneath it all. This is the river of meaning, of consequence, of value. Because you see, time travel, even if it's just the kind that lets us look back, remember, or preserve, is not just a technical challenge or a riddle for physics. It's also an ethical, legal, and cultural adventure, one that asks us not just what we can do, but what we should do, what we must protect, and what we risk losing as we learn to navigate time's strange landscape. First, let's think about the ethics of changing the past, even hypothetically. If some miracle of technology or luck let us reach back and alter history, what right would we have to do so? There's the temptation, of course, to save lives, to right wrongs, to undo regrets. But there's also a danger, a humility that comes from knowing that every change ripples outward. To rewrite even a single moment is to risk unmaking the world as we know it, to erase not just sorrow, but joy, not just tragedy, but the lessons that came after. The ethics are not simple. It's not just a matter of fixing mistakes. It's about understanding that history is woven from the choices of countless lives, all entangled, all fragile. And what about privacy? What about the rights of those whose past might be laid bare? If technology allows us to see further back, to reconstruct moments once lost, what protections do we owe to the people whose stories are revealed? Time travel, even in the form of advanced data analysis or deep historical reconstruction, can become a form of surveillance. The line between discovery and intrusion is thin. We have to ask, when does remembering become violating? When does the quest to know become an act of erasure or exposure? This grows even more urgent when we think about the future. Suppose for a moment that data could travel forward, or that records from the future could enter our present. The questions multiply. Whose consent is needed? What happens if your private choices become tomorrow's public record? Is there a right to be forgotten, even across centuries? The legal landscape grows as strange as the physical one. with questions about evidence, about liability, about the ownership of memories and the boundaries of consent. And, well, the law itself becomes a time machine, in a way. Imagine a court receiving evidence from the future, a warning, a prediction, a digital ghost. What rules would apply? Could such evidence be trusted, or would it threaten the very foundation of justice, which is built on causality and the reliability of testimony? The challenge isn't just technical, it's a matter of philosophy and trust. The very notion of law is rooted in the flow of time. Cause leads to effect, action to consequence. What happens if the flow is broken or blurred? But it's not just about privacy and law. There are economic questions too. If sensitive technology, cryptography, computation, finance can be influenced by signals from other times, the risks are enormous. Markets could be manipulated, secrets could be undone, value could vanish or explode without warning. The ethics of responsibility, of foresight, of stewardship become more complicated in a world where time's boundaries are soft. Who guards the gate? Who decides what's allowed? Who takes the blame if something from the future or from the past goes terribly wrong? And then, of course, there's the impact on our stories, on the way we dream, imagine, and understand the world. Time travel has always been a playground for fiction, for film, for myth. It shapes our collective imagination, from tales of doomed lovers to visions of utopias or disasters, from the paradoxes of Oedipus to the time loops of cinema and literature. We turn to time travel again and again, not just to escape, but to explore what it means to be human, to make choices, to face consequences, to hope. The way we talk about time through art, through story, through shared fantasy, shapes our sense of the possible and the impossible, the moral and the forbidden. And the boundary between fiction and fact is growing thinner. Science communication faces a real challenge: how to share the wonder and possibility of time travel without blurring the lines between what's real and what's just a story. Public understanding, critical thinking, skepticism, these become as important as the equations and experiments. If we dream carelessly, we risk disappointment, confusion, or even fear. If we dream wisely, we can use the allure of time travel to teach, to question, to expand the horizon of what we know and what we hope for. But, well, there are also urgent scientific frontiers. As research into quantum gravity, negative energy, and the search for natural closed time-like curves pushes on, the community is forced to grapple with new kinds of risk and responsibility. Suppose one day evidence emerges that such phenomena exist, not in theory, but in reality. How should we respond? What safeguards, what transparency, what collective decision-making are required to balance the hunger for knowledge against the need for safety? Science is not just about discovery, it's about stewardship, about the careful negotiation between curiosity and caution. And as always, critical thinking is the key. Time travel, like any other bold hypothesis, is a tool for testing the strength of our theories, the resilience of our beliefs. Paradoxes, whether logical or ethical, are invitations to probe deeper, to examine what we take for granted, to build frameworks of trust and skepticism that can weather the most dizzying possibilities. It's not just about science or law or art. It's about the way we think, the way we teach, the way we prepare the next generation for the unknown. So what does it mean, in the end, to live in a world where the boundaries of time are not as fixed as they once seemed? It means carrying both wonder and humility. It means embracing the future not just as a destination, but as a responsibility. It means holding the past not just as a museum, but as a living legacy, something to be honored, questioned, and protected. The flow of time is more than a physical law. It's a challenge and a gift. Every new discovery, whether it's a clock that ticks more slowly, a theory that bends the arrow, or a story that reimagines the very shape of history, asks us to rethink what it means to be human, to be responsible for memory, for hope, for the stories we tell and the futures we build. And, well, as we close this circle, as we reach the end of 100 facts and a dozen chapters, the journey's not over. The questions persist. The frontier is always moving. Perhaps in the next phase, we'll take each cluster of facts and dive deeper into case studies, experiments, or scenarios that reveal in detail the wild beauty and the sobering responsibility that come with traveling, however briefly, through time. So, let's keep wondering, keep questioning, keep listening for the echoes of the future and the whispers of the past. Time, after all, is not just out there in the stars, it's in here, in the choices we make, the lives we lead, and the stories we dare to imagine next. And so, well, as our journey through time and possibility draws to a kind of pause, a gentle breath rather than a full stop, I find myself thinking about how strange it is, really, that in 2025, with all our science and technology, with all our equations and satellites and data, we are still so moved by the old, deep questions. What is time? Why does it flow? Where do we stand in its river? And what does it mean to try to step upstream or to send a message across the water to another shore? We talk about wormholes and time machines and paradoxes, but at the heart of it all is something simpler, something both deeply familiar and forever out of reach. That's the thing about time. It isn't just a dimension or a number or a property of the universe to be measured. It's also a feeling, a rhythm, a pulse, a sense of before and after that stitches together our memories, our hopes, our regrets. It's not just out there in black holes or the cosmic microwave background. It's in here, in the way we grow older, the way we remember childhood or imagine futures not yet written. We live in time not just as scientists or philosophers, but as human beings, as storytellers, as dreamers and survivors and builders of meaning. And the more we learn, the more the mystery seems to deepen. Every scientific answer leads to a new, subtler question. Yes, we can measure time dilation in the lab. Yes, we can synchronize clocks on mountains and satellites. But why was the universe born with such low entropy, such a storehouse of order and possibility? Why is there something rather than nothing? And why does it change, flow, become? Why does the arrow of time point one way and not the other? And why, oh why, does it so often seem to slip away just when we wish it would linger? It's not just physics, you know. It's not just logic or mathematics. The wonder of time is also the wonder of experience. Every heartbeat is a reminder. Every photograph, every fossil, every whispered memory passed down from grandparent to child is a kind of time travel, a way of connecting, however briefly, with moments that are gone, yet somehow present. We are, all of us, custodians of stories, carrying the past into the present and sending it forward, one fragile step at a time. And as science lets us reach further into the ancient light of galaxies, into the secrets locked in rocks and DNA, into simulations that resurrect forgotten worlds, we find ourselves both empowered and humbled, empowered, because knowledge gives us tools to remember more, to understand better, to choose with greater care. Humbled, because the deeper we look, the more we see our own smallness against the cosmic tapestry. The universe is vast, and time is vaster still. Well, perhaps the greatest lesson of this journey is that time travel, in the end, is as much about attention as about technology. It's about how we notice, how we remember, how we act. It's not just about building machines or bending laws, but about cultivating a sense of presence, a respect for the stories that make us who we are. Every moment, every choice, every act of kindness or curiosity is a way of shaping the future, of sending a ripple forward in the river of becoming. And that brings us to a kind of crossroads, a place where science, philosophy, and daily life meet. We, we can dream of changing the past, of seeing the future, of stepping outside the flow. But perhaps, in the end, the real gift is to be awake to the present, to honor the connections between moments, to carry forward the best of what we find, and to let go, gently, of what must be left behind. It's not just the grand paradoxes that shape us, but the little ones. The way a scent can bring back a decade, the way a decision echoes down the years, the way history is made not only in great leaps, but in the quiet accumulation of days. We grow older, clocks tick, the universe expands, and still there is beauty in the ordinary miracle of moving forward, one breath, one word, one act at a time. So what remains as the facts fade and the story winds down? Maybe it's gratitude for the chance to wonder, to ask questions, to be a small part of the great experiment that is the cosmos. Maybe it's humility for the limits we face, for the riddles we cannot solve, for the fragility of the worlds we build in memory and hope. Maybe too, it's a kind of quiet faith that the universe is not only vast and indifferent, but also, in its own way, generous, that it gives us time, gives us each other, gives us the tools to reach out and listen and learn. And as we look ahead, the adventure is not over. There are always new questions, new mysteries, new ways to explore the landscape of time. Whether it's through science, through art, through relationships or reflection, the journey continues. Each generation picks up the thread, asks its own questions, finds its own meaning in the river's flow. Perhaps, in the end, the greatest act of time travel is to become, even for a moment, fully present, to let the past inform us without trapping us, to let the future call us without frightening us, to see the beauty in the moment as it passes, always changing, always gone, always arriving. We may never build a machine to visit yesterday or tomorrow, but we can honor the journey and carry the story forward. Well, I suppose there's something fitting in that. Time is not a clock. It's a landscape we travel through. It's not a chain, but a song, a melody we inherit and improvise and pass along. And as the song fades and the silence returns, maybe we can remember every question is an opening, every answer a beginning, every moment an invitation to wonder. So let's stay curious, let's stay kind, let's be gentle with the past, generous with the present, and brave with the future. The universe is listening, and the story is never really over. The next chapter is always beginning, just beyond the horizon of now.